Okay,
So please go ahead.
thanks.
And welcome everyone.
Welcome, everyone. It's great to see a lot of faces here today. This is our first lecture, lecture 1A for Seminar Pro Seminar of Computer Architecture. So today I'll cover some introduction and then talk about some logistics. And then I'll also go through a paper presentation to give some tips about like what we expect from you to do and how to make this paper presentation in a nice and not very difficult way. Okay, so goal of the seminar is to strengthen your understanding on computer architecture and to teach you, enable you, empower you in thinking critically, broadly, learn how to understand, analyze, and present papers and ideas, and get familiar with the key first steps in research, and get familiar with key research directions. So this is our team. So I assume you all know Mike Schwartz, and I'm Giray, the guy next to him. And then we have four TAs who will help you with your presentations here.
Also,
Yeah.
here.
Yeah.
This time.
Yeah. And there's Nahum. Yeah.
All are here. Perfect. Remember their faces.
So our main focus will be computer architecture and naturally some security as well. Actually, a bit more focus on security, I guess, at the moment. This is the system stack. On the very top, we have problems we want to solve, and then we develop algorithms, and then we implement them on real hardware, right? So it goes down to the physics level. And when we say computer architecture, a narrow view of computer architecture is here: microarchitecture, software, hardware interface. And a broader expanded view of computer architecture is here that expands up to algorithms and then go down to the devices. Everything is connected at the end. And there are a lot of abstraction layers here, but as some of you are familiar with, we keep going through those abstraction layers in our research. So this is an introduction to our research as well. So we will take this expanded view. And recently, you can see that if you do that, if you take the expanded view in computer architecture and touch a lot of layers here, then you can enable great things. As a broader definition of computer architecture, is the science and art of designing computing platforms to achieve a set of design goals that are like quite diverse here. I'm not going to go through all of them. But they all follow some fundamental principles here. Your goals can vary a lot. Your platforms can vary a lot. Your trade-offs can vary a lot. Designing a supercomputer and mobile phone are completely different things, but you can see a lot of common fundamental principles there. Today, computer architecture is interesting because it's important to enable better systems, faster, cheaper, smaller, more reliable. And these systems enable new applications, and then new applications demand new systems. And in general, we want to enable better solutions to problems that are important to like all humanity. Okay, so another thing, of course, is you can study computer architecture just to understand why computers work, if you're very curious about that. Today, it's very exciting time, and industry is in a large paradigm shift. You can see a lot of new architectures, a lot of design space explorations in both research and industry, academia and industry. And there are many difficult problems today that motivate more research in computer architecture. And there's no clear definitive answers to this, so there are a lot of ongoing research, and these problems are not fundamental solved. Okay, so this is a seminar class and a pro seminar class. So I don't know which one you registered, but we opened it for both of them with different demands. I will come to that. But our focus, like the common thing, is that we want to focus on fundamental and cutting-edge research papers in computer architecture. And there are multiple components aiming to improve your technical skills, critical thinking and analysis, technical presentation skills, familiarity with major research directions, and so on. To make the best out of this, this is our recommendation. Come prepared, read the paper that is going to be discussed, and think about new ideas, bring discussion points, questions, read other papers, be critical. Feel free to brainstorm, just throw ideas as well, and pay attention and discuss and contribute. This is a completely, not today maybe so much, but what we want in the upcoming sessions is to be interactive mostly and participate online as well after each meeting. So after a paper presentation, we will create some media for discussion, and then we invite you to discuss furthermore over there so that brainstorming can be out of this session as well. Okay. So there are some general principles of a good paper review or talk, and these are some like essentials. Basically, you need to have the title, author's venue, summary. What is the problem that this paper is trying to solve, and what are the key ideas in the paper? What are the key insights? What are the key mechanisms? What is the implementation? What are the key results, key conclusions? You need to summarize all these when you go through this paper review or presenting your review, basically. And then you need to focus on the strengths, list them. These are some examples. Does the paper solve the problem well? Is it well written? So you need to answer these questions, and there will be more examples of strengths as well. And then you need to focus on the most important weaknesses. This is where you need to think really critically so that you will find the devils in the detail and all the weaknesses of the paper, and those will be the starting points for your idea generation, brainstorming, and discussion points. And then you should share your thoughts and ideas, and you should always keep asking the question, can you do better? And discuss your ideas and state your takeaways. And then at the end, we need to have some discussion starters and questions. These are the material that you'll prepare to have a fruitful brainstorming discussion after the paper presentation. So it's not just presenting the paper. So as I said earlier, when you present a paper, you need to start with the problem and goal, and then go through the key ideas, solution, novelty, mechanisms, implementation, major results, and takeaways and conclusions. This is all about what is presented in the paper, right? So this material is already exists in the paper, and you need to deliver it in a nice, concise way. So this part, what we expect to take is around like 20 minutes. It shouldn't exceed. So it's not really like super hard limit, but you need to aim for this, and it's important to wrap up everything in a short amount of time so that we will be on schedule as well. So it shouldn't exceed 20 minutes ideally. And then you will list the strengths and weaknesses of the paper. This is 5 minutes, but it's actually more than that. You will see next. So you need to talk about the paper's significance in the literature. You need to talk about new ideas and problems that are coming up from this paper. And then you need to brainstorm future ideas, look into future research directions, and you should go through your discussion points as another 15 minutes. So in total, we have 40 minutes, and only half of that is summarizing what the paper says. And the other half is it's sort of your intellectual property, basically. You need to generate it. Okay. So there are some advices, of course. So when doing the paper reviews and analysis, you should be very critical. You should always think about better ways of solving the problem and also the related problems. You need to question the problem itself as well. Is it really a problem? Is the motivation of the paper a real motivation? Are you convinced that it is actually a problem? You need to read the background papers. So in general, when you do paper reviews, it's usually like you need to read the past as well to understand the state of the art before this paper. But in this class, we also have some papers that are like fairly old. And if you end up being assigned to those, if you choose them, then there will be also follow-up works built on top of these papers. So to understand the impact of that paper that you're presenting, you need to look into both past and future. And the most important thing is the critical thinking and analysis. So this is how things progress in science and engineering in general. So you need to always be skeptical and criticize every claim in the paper, every statement over there. And we will also provide some sample text of reviews. There are some nice examples. But I want to highlight one thing when it comes to analyzing papers. So when you identify weaknesses, it's completely fine to identify all sorts of weaknesses. All the papers have weaknesses, so it's better to talk about them. But you shouldn't put much focus on certain types of weaknesses that will not lead to fruitful discussions. That are called as like rat holes in these sources. So you can always say that, okay, so this particular computer architecture work came up with this mechanism, and then they evaluated their performance gains on this set of workloads, but why not more workloads? So you can always say that, yes, that is correct, but it doesn't necessarily take you to a good brainstorming session for many papers, essentially. Because even if the paper already tests 100 workloads, then you can say, oh, what about the 101st workload? Or if it's 1,000, you can say 1,001st workload. There's no end to that, right? As long as the major claims and the takeaways in the paper are substantiated with data, then it should be okay. You can still complain about that as long as it's just like short statement, basically. We shouldn't get lost in these rat holes. There is an online resource from a Stanford professor, Kevin Fatalian, on about giving clear talks. I recommend it. There are some rule of thumb kind of advices here. So from time to time, I actually go through those slides to understand if I'm doing something wrong, and I recommend that to you as well. And yeah, so this is an example from those slides actually. So on the left, you see a painting of Salvador Dali when he was 22. It's just like a basket of bread, I think, right? Something like that. And it's sort of a boring kind of painting, right? On the right hand side, you see like something more creative and something really like interesting. And it's happened at age of 53. So the principle that Kevin actually highlights in that slide is that you need to learn the basic principles so that you can later on consciously choose the breakdown. So there are some basic principles of explaining a concept or presenting a paper. You need to follow or learn those principles at least. And then when you decide to not to follow those practices, it should be some conscious decisions. So I have a talk on YouTube actually from ETH Zurich that was given in another seminar in computer architecture class that I presented the paper and then went through some discussion and gave some tips as well. So I just put the link here so that you can also take a look at that to get some advice, basically. Okay, so far it's I guess all until the end of introduction. So are there questions until this point? Okay. I guess people are more interested in logistics and grading, so I'll go into that. So we're expecting 3 deliverables, and there's a +1 as well. +1 is participating in discussion during the session, so you need to be active. You shouldn't be just sitting silent. That's a given, so I didn't list it here, but other than that, we have 3 deliverables. The first one is the critical paper review talk. So most of you, I guess, already did the stated your preferences about the paper presentations, right? So we will assign you the paper, and this is that paper. You need to prepare a talk and then give it in this lecture. As I said earlier, like it's like 20 minutes summary, 5 minutes strengths, weaknesses, and then 15 minutes of discussion at the end. And then you will have a critical paper review report. This is about your paper review. So you're assigned a paper X. So you presented paper X, and this report is the report of that paper X review, actually. So this will come in like 2 versions, actually, but I will come to that later. So the third deliverable is a literature survey. And this focuses on a paper that is not presented by you, but presented by one of your classmates. So you can choose which one. And then you need to prepare a literature survey related to that paper. Okay, so this is an advice, and there are some compulsory items as well in it. So when you prepare your critical paper review talk, you should know that good presentation takes time, and you need to start early. Some of your presentations will be earlier than some others, so we will also take that into account. Don't worry about that. And you need to study your paper. You need to carefully look up the terms, read the cited most relevant papers, not only your paper. You need to critically find the limitations and the flaws in the paper, and you need to think creatively and think for improvements. Always ask, can we do better? And if there are some open source material, you can try it. For example, it will give you a better understanding of what the paper is talking about, and you study the follow-up works if there are. So for the papers that are published in 2026, probably there are not much follow-up works, but there are also papers published in like early 2000s, for example, and there are a lot of follow-up works, so you need to take a look at them as well. And you need to consult with your mentors, so you will assign you mentors as well based on the paper that you chose. And you need to consult with them if you have any questions. And now you need to create a draft of the presentation, explain the motivation for the work, clearly present the technical solution and results, and include a demo if appropriate, not appropriate for all of the papers. And you need to outline the limitations or improvements of the paper and focus on the key concepts. Do not present all of the details. And now you need to meet your advisor or mentor and prepare for the meeting. So schedule early because so we have 4 TAs here. They're more than happy to help you. We are also happy to help you, but all of us are like quite busy people. So give us time to schedule the meetings as well. So send slides in advance and write down your questions so that it will be a fruitful meeting, and make sure that you address the feedback you got from your mentors. And there is a mandatory item here. You need to have at least 1 meeting with your assigned mentor so that this will happen before your presentation, and you will fix your presentation and prepare your report based on that. And it should be latest the week before the talk. And this will be like quite soon for some of you. Okay, so this is the second item, critical paper review report. So what we expect here is pretty much the same material as your presentation, actually, but in a written form. So this is a critical review report of your paper and follows the same structure as your talk. You need to keep it concise, not really strict formatting requirements or like minimum number of pages, maximum number of pages, but just keep it concise, not very long. It shouldn't waste your time. It shouldn't waste our time as well. But we want this in a written form. So it will include your paper summary, your critique, your discussion points, and this is your first version. And this first version is due sometime in the mid-semester. It might be before your presentation or after your presentation, like the first version deadline is in the middle. And then there will be a version 2 that we will use for grading. So version 1 is just for giving you feedback. Version 2 is for grading. And we want you to include more improve your discussion basically based on the brainstorming you had during the session and after the session online as well. And then there's literature survey. So this is based on a paper presented by your classmate, not you. And it follows the same structure as your talk again, but it contains two more sections, each summarizing a number of other papers. One of them is state of the art before the presented paper, and the other one is state of the art today and your projection into the future. What you expect to happen in this narrow field of research. And this is due 2 weeks before the last day of grade submission, so I need to check the date. But yeah, so this is like a long-term due basically. And this is compulsory only if you're registered to the seminar class, but it will be just bonus points for well, everyone here. Actually, this is gonna be more clear here. So this is the grading rubric. This is the like percentages of your grades, where they're coming from. So for the seminar students, they need to submit all these four materials. For pro-seminar, literature survey is not a must. And if you fulfill everything here, then you can submit more literature surveys as bonus to collect bonus points, basically. Okay. So tentative schedule is like this. We will meet once a week, except some weeks that I will specify. The meetings will happen on Mondays. We will have two presentations per session, 40 minutes each. So we will have 10 minutes break in between, and we will wrap up in 1.5 hours. And meeting time is on Mondays at 3 p.m. and we need to wrap up before 4:30. So we will start sharp at 3 p.m. So please be here before that. And regarding the paper assignment, I already shared the list of papers, and we already uploaded all the papers in PDF form under this materials link. You can access them here on the CMS webpage. And you're allowed to suggest some papers that are not included in the list, but they are subject to our approval, of course. So you need to tell us about them. We need to evaluate them. And you should bid papers online. So this slide is a bit stale for some of you because you already did that. And in general, please check your email and be responsive. And the assignment policy for paper assignment will be first come, first served if there are conflicts. And the due in the announcement was May 4th. It is still May 4th. But given that many of you already submitted your preferences, I'm suggesting to pull it earlier to this Thursday so that we can also do the assignments earlier and give you more time for preparation. Does it make sense to all of you? If somebody objects, I guess we cannot do that because I already announced it as May 4th. Okay.
When you object.
Cool. So then the due date is this Thursday. And this is like small categories of the paper by the year. And so we cover like things starting from CPU fuzzing to like microarchitecture security, upcoming architecture paradigms, processing near, in, or using memory or storage, memory security, memory reliability, trust execution environments. So we have quite a spectrum here. You will see them in the paper list if you didn't check it. So on April 22nd, we released the paper list, and today is April 27th, so we are having this session. So there are some important dates here. So we are lucky that only the Whit Monday has a time conflict with our class day, so there will be no session here. And next week as well, we will not have a session, so that it will give you time for preparing your talk. And we will have student presentations in all other weeks. And we tend to keep these June 29 and July 6 unoccupied so that we can attend ISCA and Euro SMP. These are some of the very important conferences in our field. So if you're planning to drop the class, please drop it early so that we don't have to schedule some presentations in in these weeks. And yeah, these are the deadlines. So for your report version 1, it's at the end of May, and report version 2 is the last day of the class is basically July 14th, I believe, in this academical calendar. Okay. Here is the policy for using artificial intelligence. The rule of thumb is that AI is a tool and it doesn't replace you. And you are the sole author and you are the responsible entity for the presented and submitted material. And yeah, we will not tolerate hallucinations. You need to pay attention to every single word, even punctuations. And if in extreme cases happen, we might invite you for some oral exam as well. Using AI is okay in a limited scope. So to fix your grammar, to polish your material, of course, it's okay. And of course, you need to vet everything. You can also, if you feel like you want to do that, you can brainstorm with some AI tools, but you need to fact check everything. So you shouldn't trust anything that any of the AI tools tell you because they can hallucinate really well.
Especially in this field of research.
Yes.
Because they don't have so much training data there, and they will come up with a lot of wrong stuff.
Yes.
So here it's even more important than in other fields. They will talk about the greatest achievements in computer architecture don't exist.
Yeah. So when you use AI, do not trust, fact check everything. Make sure that terminology is correct. And another rule of thumb, AI is great, but you should be greater than that. And the technical depth of the final submitted material should be deeper than what AI can generate by itself. And this is the end of my slides for introduction and logistics. It's 34 minutes. That's good. Oh, it's actually 28 minutes. Okay, we have more time for the paper presentation. Before starting with that, I will just give like a 10-minute break, but even before then, I can answer, or Michael can answer some of your questions.
Are there questions?
Are there questions?
For the presentation session, so it's 45 minutes, and we're responsible, if it's the assigned paper of ours, we're responsible for the whole 45 minutes. We have to present it, then we have to do the particular review, and then we have to lead the discussion for 15 minutes, right? Okay. So should we already drop all of our critics and stuff in the critical review section, or should we use that to lead towards the discussion and retain some critique for the discussion section?
So it's all together anyway, actually, right? So after 20 minutes of presentation, you go with the strengths and weaknesses, and then you gradually move to your discussion points. So your weaknesses and your discussion points will be like quite relevant anyway, right? And
yes, but do I have to get all of my critique on the final critique section already, or can I defer some of that to the discussion later on?
So in my mind, it's more like you keep it high level in the critique section of that, and then in the discussion part, you will elaborate on that more. Yeah. Maybe you will need to prepare like additional slides to remind people what you were talking about. And then it will be more like future looking rather than limited to this paper scope. So in one of them, you can say that, okay, yeah, this idea doesn't work under these circumstances, right? And then the discussion point, you can say, okay, how can we make it work under these circumstances as well?
Question? The discussion part of the last 15 minutes of the 40-minute presentation, or after the 40 minutes?
The last 15 minutes of the 40 minutes. So yeah, I can bring that up.
We have 90 minutes split into 2 sessions, so it's 45 each, everything.
Yeah, but assuming that we will have like 10-minute break, and then it's like 40 minutes.
Yes.
If you go overtime, then we eat
break.
up from the break. Yeah.
When we register in the LSF?
Yes.
Yes, that should be open registration now, and that's within the next 3 weeks. So do it as soon as possible.
Yeah, I forgot to announce that. I will announce it.
True. And
Yeah.
yes, very good point. You all have to register in the NSF, so you can actually get a grade for that. If you're not registered there, we cannot give you a grade. You also cannot circumvent that anymore. It's not allowed. Yes.
Was there a way before?
Yes.
Okay, then.
So make sure you are registered.
Other questions? Right. Okay. Then let's take a 10-minute break and then I'll present a paper after that. Okay, everybody, let's start. Now I'll give a presentation of a paper just to show some example. Of course, you don't have to strictly follow what I present here, but it's just to give you some more idea about like what we expect. So this is the name of the paper, Break Hammer. It was published in Micro in 2024, and it's about enhancing row hammer mitigations by careful throttle suspect threats. So here's the executive summary. So the problem definitions goes like the DRAM continues to become more vulnerable to row hammer, and this is because DRAM density scaling, and when you do that, row hammer preventive actions are becoming more time consuming and they block access memory more. And there's an exploit in theory you can do by mounting some memory performance attack on this property. So you can intentionally trigger these row hammer preventive actions that I will talk about what they are to block memory accesses for longer time windows. And this is the problem that this paper tackles. And our goal here is to reduce the performance overhead of such mitigation mechanisms by reducing the number of them being performed without compromising the system robustness. And our key idea is to throttle the threads that frequently trigger row hammer solutions. And our mechanism is called break hammer. Break hammer observes which thread is triggering these row hammer mitigation preventive actions frequently. And it identifies the threads that trigger them. And it reduces those threads' memory bandwidth usage. And break hammer significantly reduces the negative effects of row hammer mitigation mechanisms on performance, energy, and fairness. And its artifact is open sourced on GitHub. Okay, so I just went through an executive summary, and this is what an executive summary looks like. It's the summary of the paper in a nutshell. Of course, sometimes it's not very clear. So I didn't give some background about what row hammer is, what DRAM is, for example. And in many cases, you need that background anyway. But it's just for the sake of example here. And it tells what the paper is about and sets the expectations from the audience or the reader. So it serves the same purpose as the paper's abstract here, right? So it's very short and it just covers the main points of the paper, just tells the narrative in the paper in a very high level, and helps the reader or the audience to decide if they get bored, if they find it interesting, if they want to read the rest of the paper, if they want to pay attention for the rest of the talk. So it plays a key role in that aspect as well. So I usually find it as a good practice to give this early in the talk Sometimes, as I said, like you need to use some background before this, so maybe 2, 3, 4 slides of background, and then do the executive summary. It's you can shift it in presentation anyway. Okay, so I'll continue talking about the paper. So this is the outline of the paper. Let's start with the background. So this is how DRAM modules look like. So on the left-hand side, we have the CPU. On the right-hand side, we have a DRAM module picture. And they are connected through something called DRAM channel. They communicate over DRAM channel. In the DRAM module, we have multiple DRAM chips. And within each DRAM chip, we have multiple banks. Each of them have an arrays. And within a bank, you organize cells in a two-dimensional array. These circles are DRAM cells. And a DRAM cell looks like this in the circuit level. It's a capacitor and an access transistor. And you have word lines that you use to assert and enable these access transistors. So when you want to access the data on the capacitor, you assert this word line. And then when you assert them, the access transistor is on and the capacitor is connected to those vertical lines that are called bit lines. And through those bit lines, they're connected to some local I/O structure called sense amplifiers or row buffer. So in DRAM, you access data in a DRAM row granularity. So if you want to access data from row 2 here, you first need to assert the word line and open row 2. And once you're done and you want to access another piece of data in another row, you need to close this. If you perform this open close operation many times, then you observe bit flips in nearby unaccessed locations. And this is called row hammer. It's a prime example of read disturbance. So you read a row many times, and then that action itself induces bit flips in other nearby rows, even though you didn't access them, even though you didn't write anything to them. And if you do that many times, then you observe more bit flips in more rows. Here, the row that we keep opening and closing or hammering is called aggressor row, and the rows that are affected are called victim rows. And the minimum number of activations that cause the bit flip is called the row hammer threshold or NRH in the rest of this talk. So with DRAM technology not scaling, these cells get smaller in size and they get close to each other, but you still operate at the same voltage level. They drain similar power. And then with this technology not scaling, your read disturbance effect gets even worse. And when we look at the data from the field in the not last 10 years anymore, from 2013 to 23, we have 2 orders of magnitude reduction in the minimum activation count needed to induce the first bit flip. And today it's critical to prevent read disturbance bit flips effectively and efficiently for highly vulnerable systems. So here I want to highlight another thing. So what I show here is a takeaway box. I recommend you to use it because it explicitly tells the audience what is your take from the slide and what they should remember. And it's a nice way of conveying your message explicitly to the audience. Okay. So when we look at how we prevent row hammer, there are many ways of actually preventing row hammer. Once you detect there is row hammer like access pattern and you want to protect rows, you want to avoid bit flips, you can do some refresh operations preventively. You can migrate rows around. You can proactively throttle some accesses, and you can do other things as well. And this paper, we focus on these 2 mitigation preventive actions, preventive refresh and row migration, because these are the most popular ones in the state of the art today. Okay, this is how you do preventive refresh. You identify this aggressor row, and then you perform this refresh operation and the victim rows before they observe bit flips. So row hammer it works through exacerbating the charge leakage on these victim rows, and you restore the charge back when you do refresh, and then you just reset all the effects accumulated so far. The row migration goes like this. You identify this aggressor row, and then you move to in a different physical location. So it's not nearby those previous victim rows anymore. So those victim rows will not be disturbed furthermore. Okay, let's go with the motivation. So when we look at row hammer preventive actions, we observe that they are blocking and they are quite time consuming. So when you want to access data and you send an activation command, for example, you cannot do that if the memory bank is busy with another row open. And it creates some conflict in the DRAM bank level, and you cannot perform this activation operation. So if you're refreshing a row or accessing a row, you cannot access other rows. And refreshing kilobytes of data can block accesses to gigabytes of data. So this is a availability issue in a broader sense. So here we look at how row hammer mitigation mechanisms affect the system performance. So on the x-axis here we have the row hammer threshold. It's getting worse when we go from left to right because you become more vulnerable to row hammer. It becomes easier to induce row hammer bit flips, and your mitigation mechanisms need to react more aggressively. And on the y-axis, we look at the system performance in terms of normalized weighted speed up. This is a performance metric used for multi-core systems, and lower is worse here. Okay, so different colors here represent different row hammer mitigation mechanisms in the field: Hydra, RFM, Para, and Aqua of that time. So 3 of them are based on preventive refresh, 1 of them is based on row migration. And here, if you look at the a bit exaggerated side of the plot for row hammer threshold of 64, you observe 19% performance degradation for Hydra, 66% for Aqua, for example, and you see the other bars over there as well, somewhere in between. So it shows us that row hammer mitigation mechanisms incur increasingly large performance overheads as row hammer threshold decreases, and you're not doing this for something useful, actually, right? If you think from the user's perspective, you're paying for this performance penalty just to make the things work, just to make the computer operate, right? So ideally, you shouldn't have no overheads. It should be zero. Okay, so I want to highlight something here while presenting this plot. I'm not sure if you paid attention, but basically, oh, interesting. Okay. So this is a bad example at the same time because I have a white shadow here in front of this text, so it's not good. But I will fix it later on. So you need to first start explaining the plot before making the observations. So this is what I did here. Like first explain what is on the x-axis, what's on the y-axis, what happens when, like which way is better, which way is worse. And then what are the colors represent, what are the error bars represent. I didn't talk about it. It wasn't a good example, but you should talk about it in that case. You need to highlight the observations. And for highlighting observations, you can use some transparent boxes. These are your friends, and they can help you highlight stuff in a nice way. And at the end, it's a good practice to, again, give your key takeaway in a key takeaway box. Okay, let's go back to the paper. So we're talking about a variation of memory performance attacks here. So if there's an attacker that knows your row hammer mitigation mechanism, and your row hammer mitigation mechanism already has some high performance overhead, it performs blocking and time-consuming operations in the DRAM chip. So this attacker can intentionally trigger these preventive actions and block accesses to your main memory. And this goes to denial of memory service at the end, right? If you exaggerate it. Okay. So the problem is this high performance overhead of these operations and the reduction in DRAM bandwidth availability. And our goal is to reduce this performance overhead so that we will not have this availability problem when we deploy these row hammer mitigation mechanisms. This is our mechanism, break hammer. The key idea is to detect and slow down the memory accesses of the threads that perform that trigger these row hammer preventive actions very frequently. So you basically identify who is the attacker. This is your suspect thread, and then you reduce that thread's memory bandwidth usage. It works in an epoch-based manner, so there are like time windows, and you define a throttling window as like the time between two preventive refresh operations, and then you observe which thread performs activations how many times during this time window. And you keep a score of each thread here. So in your system, you may think that you have a lot of threads, hundreds of threads, okay? But when you go to the hardware realm of the things, then you have only like a bunch of threads, right? So maybe you have like 16 threads, or 32 threads, 64 threads. Depends on like what kind of hyper-threading is implemented over there, how many cores you have, but your number of hardware threads is quite limited. So you implement a counter for each thread, and then you keep a score of the number of activations for each thread. And then you somehow identify some anomaly among these threads, and then you say that, okay, this is my suspect thread. And then you reduce the bandwidth usage of that thread. And I will get into how to do that in a little bit. First, how to observe row hammer preventive actions. Break hammer tracks the number of row hammer preventive actions each thread triggers, and it is counting a score based on that. So let's say in this time window, so each one of these T's correspond to an activation. So T1 is a row activation from thread 1, T4 is a row activation from thread 4, for example. And you have, for example, here 4 different activations coming from thread 4, 2 activations from thread 1, and so on. And then a row hammer preventive action comes at some point. Now you attribute the cause of this row hammer preventive action in a proportional way to each of these threads in this mechanism. And it's a high-level description, of course, and I will give 2 examples to show how it works, because this is a mechanism that works in tandem with different row hammer mitigation mechanisms, and this the way it works can change from mitigation to mitigation. So here is the first example, PARA. PARA is a mechanism that was published in ISCA 2014, even though it says 24, it should be 2014. So break hammer cooperates with PARA. This is how PARA works, as like in the original proposal. Whenever an activation happens, it generates a random number, and then compares that random number against the threshold. And if that number is larger than a threshold, it performs a refresh operation. So the more activations you perform in the system, there's a higher probability that you will cause a refresh operation about that. Okay, so what we do here is that we track the row activation count of each thread between 2 preventive refresh operations. So until the refresh operation comes, like you have different numbers from each thread, and then you just like proportionally attribute the responsibility of this preventive refresh to each of these threads. Okay, so let's go for another example, PRAC. PRAC is an industrial standard today that was published in a JEDEC document in 2024. In this mechanism, DRAM itself internally maintains an activation counter for each DRAM row. And these activation counters just increment whenever you activate a row, very straightforward. And whenever they reach to a critical threshold, DRAM chip sends a backoff signal back to the CPU, asking for time to perform preventive refresh operations. And then CPU sends a command called RFM, and then it gives enough time for the DRAM chip to perform preventive refresh operations. So here, what breakhammer does is that it observes this backoff signals, and then attributes the scores between these 2 consecutive backoff signals to each thread based on the number of activations that they perform during that time window. So these are 2 examples. This paper also integrates breakhammer, their proposal, with 6 other row hammer mitigation solutions, so 8 row hammer mitigation solutions in total. So there are more details in the paper. I will not cover all of them because it will be boring and it will be quite time consuming. But for now, yeah, we will be just going with that 2 examples. But you get the idea. You just count the number of activations per thread, and then you make the threads responsible of the preventive refresh accordingly. Okay, so how do you identify the suspect threads? So you have a table at the end. You have the scores for each thread, and then you want to understand if there's an anomaly. If you look at this example, these numbers, thread 4 is like an outlier in this distribution, right? What they do, or we do in this paper, is that we first apply a minimum score threshold. So below the score, we don't care if there's an anomaly. It's a low memory intensity, so we don't care about that. But above the score, we look at the distribution of each thread's score, and we get the maximum deviation from the average score. So here, with 50 activations, thread 4 is our suspect thread. And then we identify it as a suspect thread, and then we go with the throttling, targeting the request from this thread 4. Okay? So how do we do the throttling? So Breakhammer reduces the memory bandwidth usage of each suspect thread in the following way. So in the last level cache of your system, it's a shared resource, it's a shared cache, right? And then it's the last place that you go before going to the main memory. And in this LLC, last level cache, what we implement is a maximum count for cache miss buffers. So when you want to access data, you go to and you end up going to LLC because you miss in the closer cache levels. You go to LLC, you check if the data exists in LLC. If it doesn't exist there, then you need to allocate a cache miss buffer, or also known as miss status holding registers, MSHRs. So you allocate one of them for this request, and then you send request to the memory. So to throttle the memory accesses from a suspect thread, we apply a threshold, a quota, to the number of cache miss buffers that a thread can allocate. So here, for example, with this numbers allocated for each thread, suspect thread sends another request, and then now it hits quota. And then when it sends another request that will miss LLC, it cannot allocate a cache miss buffer. So the suspect thread stalls itself, right? It cannot make progress because it cannot also allocate cache miss buffer. So it just stalls there. But the other threads can still allocate more cache miss buffers. So their memory requests go through the memory channel, and it's just business as usual for the other threads. But for the suspect thread, it's a different story. Okay. So Breakhammer restores the memory bandwidth usage. So after some time, so this throttling is only temporarily. So in a throttling window, you identify that a thread is suspect, so you throttle it. And then in the next window, let's say the thread stops acting malicious. So you do not identify it as a suspect thread, but you still continue throttling. And then after that throttling window passes, memory bandwidth usage is restored, and you do not apply the quota anymore. And then your thread is considered as benign again. So it's just a design decision for this mechanism. Okay. So this is how the mechanism works. In high level, I skipped a lot of details. And let's look at the evaluation methodology. So this is a simulation-based evaluation methodology. So we use Remulator and DRAM power here to measure the system performance and DRAM energy consumption. Breakhammer is integrated with these 8 mechanisms, and we test 4 core workload mixes from different benchmark suites, and we look at the workload mixes where there are like 3 benign programs running with a rowhammer attack, and also mixes with all benign workloads, and 90 of each of those mixes, so 180 mixes basically. So when we look at the under attack results, this is the more interesting part. So here we're seeing the result from one mitigation mechanism, PRAC. So I already talked about PRAC, right? Okay. The animation is not following. Okay. I hope it's fixed now. So on the x-axis, we have the rowhammer thresholds going down from left to right. And on the y-axis, we have the number of preventive actions normalized to the this 4K point basically. So this plot basically shows how the number of Rowhammer preventive actions change when we reduce the Rowhammer threshold. For two mechanisms here, one of them is PRAC by itself, and the other one is PRAC integrated with Breakhammer with this throttling mechanism. So as you go from left to right, things get worse, and higher is worse as well because we perform more preventive actions. So the blue curve shows no Breakhammer case, and the orange curve shows with Breakhammer case. And you see that when we reduce the Rowhammer threshold from 4,000 to 128, there's like 34x increase in the number of preventive actions you perform in the baseline, like no Breakhammer case. And if you apply Breakhammer with this mechanism, then you reduce the number of preventive actions at this point by 80%. The behavior is similar across different mitigation mechanisms, and you can significantly reduce the number of preventive actions performed across all mechanisms. Here's another plot, similar actually, but now we are looking at a complete different thing. So on the x-axis, we have the memory latency percentile. So we care about how the memory latency in the perspective of the user changes. It's a distribution, right? So you don't have a constant memory latency, and this is an S curve of your distribution. So going from 0 to 100, we include like more and more memory accesses in this population, and then we show the maximum latency for each point. Okay, so here again, if the memory latency increases, things get worse. So the system gets slower, and we have three curves here. Blue curve is PRAC without Breakhammer. Orange curve is PRAC with Breakhammer, and the black curve is no defense. So if there's no defense, then you also have this variation in your memory access latency because of the locality of your caches and the row buffer locality and different things in your system. Memory latency varies a lot. Okay, so this black curve shows how it varies, and when you look at the here this point, in this point, we see that 50% of the requests are served within 200 nanoseconds, right? And if you look at with Breakhammer, it's much lower, and no defense is in between. Okay, so we can say that Breakhammer significantly reduces the memory access latency across all mechanisms, and in many cases, you even see that the memory access latency, the orange curve, is below the no defense case, and this is caused by throttling a suspect thread and opening up more memory bandwidth for the concurrently running benign threads. Okay, so there are more results. Maybe I shouldn't cover all of them because in the interest of time, but yeah, I'll just give the high-level observations here. So when we look at the system performance, again, Breakhammer significantly increases PRAC's system performance when PRAC is enabled in a system. And it is the same story for all these mechanisms. So here the orange bars are higher than the blue bars, showing that Breakhammer speeds up the system. And here we look at the impact on the DRAM energy consumption. Again, on the x-axis, we have the Rowhammer threshold reducing and getting worse from left to right. And in this case, lower is better because we want to consume less energy. And here the comparison is again PRAC alone and PRAC with Breakhammer. And now we see significant reductions in DRAM energy consumption as well. And the same story for the other mechanisms too. So we can take a closer look into each of these results if it comes to that, but we don't have to cover all of them in this presentation, right? So if we summarize the under attack case evaluation, Breakhammer significantly reduces the performance and energy overheads of existing Rowhammer mitigation mechanisms when a memory performance attack is present. Well, it's an overclaim actually over there when a memory performance attack based on Rowhammer mitigation mechanisms is present. Breakhammer accurately detects the suspect threads and effectively reduces the memory interference caused by the suspect threads. When there's no attack, don't worry, I'm not going to show you a lot of plots because we can summarize it like this. Across 94 core benign workload mixes, we observe that Breakhammer slightly improves memory access latency, system performance, and DRAM energy efficiency. There are no slowdowns that we observed. And there are more analyses in the paper. So I guess in your case, you might want to go through more results, depending on what you want to focus in the paper that you're presenting. But here I'm just gonna mention these and I'll skip it. So there are more implementation details about how to reset, how to track software threads, how to throttle accesses coming from DMAs and systems without caches and different configuration parameters. There's a security analysis that I don't want to go through because some math included as well. So it will take some more time. And there are more performance evaluation results as well. Okay, so this is the paper. There's a QR code and the archive link is there. And in conclusion, the key exploit that this paper tackles is the memory performance attacks based on Rowhammer mitigative preventive actions. And the key mechanism is Breakhammer that observes the triggered Rowhammer preventive actions, identifies which threat triggers them the most, and then reduces the memory bandwidth usage of that threat. And under attack, it improves system performance and energy consumption. And under no attack, it has very negligible effect on the system. And its implementation is open sourced and artifact evaluated. And that's all for the paper presentation. So far, if there are questions, I can take them or I'll just continue with the rest. Okay, I'll just continue. So in terms of strengths, this paper clearly tackles an important problem. There's a lot of motivation in the paper about how Rowhammer mitigation mechanisms hog the performance and consume energy a lot. And Breakhammer is a lightweight and effective mechanism. If you think about it, you just implement a counter per thread, and it's per hardware thread, so it's just a bunch of counters. And Breakhammer can be integrated with many existing Rowhammer mitigations. This is a claim made by the paper and demonstrated on 8 use cases. And the authors already explain an open source integration with 8 mitigations. Evaluation shows that Breakhammer alleviates the negative impact of Rowhammer attack on system performance and energy consumption and does not slow down the benign workloads. Breakhammer's implementation and evaluation scripts are open source. You can make the list longer. So these are the things that came to my mind. I didn't actually spend a lot of time on this, so there can be more things. When it comes to weaknesses, the memory performance attack is not demonstrated on a real system. This is a weakness. So all the evaluation is based on simulations, and you can actually attack the motivation of the paper because it's not clear if you can do the same thing with the mitigation mechanism already deployed in these machines, for example, right? So it's something that is missing in the paper, and it's definitely a weakness. Breakhammer is hardware level mechanism. It doesn't have a good scope of everything going on in the system. If you remember the system stack from the very beginning, like in this slides, in the earlier slides, so it only looks at what's going on in the memory controller and last level cache a little bit, right? But it doesn't have the notion of the software threads, processes, users, address spaces. These contexts do not exist for Breakhammer. And it cannot track an attacker if the attacker does this attack using multiple threads, multiple processes, for example. It can keep a low profile and then bypass Breakhammer. So it's a weakness of the mechanism as well. As a memory controller-based mechanism, Breakhammer cannot observe the internals of in-DRAM solutions. So, okay, we showed it how it works with Prac. Prac is an in-DRAM solution. But going forward, we need to also talk about processing in memory kind of architectures. There's like one of the new computation paradigms. And over there, you do not have much option of throttling memory accesses. And those memory accesses, most of them are even transparent to you. So, I mean, to Breakhammer. So Breakhammer does not even cannot even observe what's going on in that manner. In the way that it's proposed in this paper, you can always adapt it to new upcoming architectures, right? But this is a weakness as well. So majority of the plots in the paper are bar plots that are not very easy to read. So this is a complaint about how the writing of the paper is. You can complain about those, of course. And you can make the list longer as long as you avoid some rat holes. Okay. Please keep in mind that every work has strengths and weaknesses, especially papers that are filtered in our list of papers are there because they have some significant merit and they have good discussion points as well. We had to exclude some papers because they were not leading to very fruitful discussions based on our earlier experiences. It doesn't mean that the papers excluded from this list are not good. It's just like this is a nice filtering. You should be able to find strengths in the list of papers here. Okay, so they should emphasize their strengths already anyway. So the paper should be telling about it to you already. It's very easy to find in that case. And there's always room for improvement for each paper, right? Even for the best of the best paper, there will be weaknesses. If you come and say that, oh, I couldn't find any weakness, the paper is awesome, and it's like strong except nothing comes to mind. It's not a good critical analysis. Then it means that you're not critically thinking. And some papers even acknowledge their own weaknesses. They have a limitations section, for example, that they talk about their weaknesses. They can give you some clues. And many weaknesses are not obvious. And some papers try to hide their weaknesses so that they can get accepted in some conferences, right? And but you have some advantage here. You have your own brain. You can think about it. You can find your weaknesses, not your weaknesses, paper's weaknesses. And you can also use other people's brains. How you do that? You can check the arguments in the paper that improve the paper, arguments in the papers that build on top of the paper that you're critically evaluating, right? So, for example, in this Breakhammer, if you go to Google Scholar, type Breakhammer, the paper appears, and there's a small link here that says it's cited by 26 other works. Okay, so if you go through the list of these papers and then search how they mention Breakhammer, then, for example, you can find this paper that has this paragraph in the related work, and then says that Breakhammer is not great because it depends on prior Rowhammer solutions for mitigation, and it requires microarchitecture modifications such as changes to caches, to propagate thread information, to throttle and logic, and in the memory code. Okay, so there's this modifications in the hardware, of course. This is a weakness of the paper, so you found the weakness of the paper, right? And then you need to also look at this paper if they provide a better solution to that, of course. It's for completeness. And you need to be really skeptical about those papers as well. Some of them can make some false claims about some earlier works. They can be some manipulative arguments as well. So you need to practice caution, basically. Okay. Let's move to discussion points and okay. I'm already in my last 3 slides and we still have 12 minutes. So that's great. Okay. So, okay, I didn't animate the slide. That's my mistake. So I want to first show some bad examples to discussion points. So first of them, okay, Rowhammer is a problem for DRAM. What about other memory technologies? So it happened in the past in some incarnations of this seminar class in my previous place. So this is a good discussion topic in general, right? You should maybe pay attention to emerging memory technologies. There are many of them, but it is not the discussion related to this paper, right? This paper's scope is not that, and it's a discussion topic for another day. So what are the mitigation mechanisms integrated with Breakhammer? Discussion. So this also happened. Like the speaker goes on stage and then explains all these, and then asks this question. So this question is already answered during the presentation, and this is more like a quiz question for the audience, right? And it is not good. Like this discussion session is not really about testing the audience if they paid attention or not. It is more about coming up with fruitful brainstorming discussions and finding good ideas that can lead to future works, basically. Another example, row hermetization mechanisms incur higher performance overheads with increasing DRAM density. So should we stop scaling DRAM density? This is another like philosophical question. So, okay, you can discuss that in some other settings as well. But yeah, it's again like out of scope and it's very open-ended. And it doesn't really go anywhere, right? So should we stop scaling DRAM density? Okay, somebody from the audience says yes, some other person says no, and then they argue. Okay, but it doesn't serve the purpose, right? It doesn't go to how can we advance the state of the art. And you can even argue that it's backwards looking. Like if DRAM density is already continuing, and it obviously gives a lot of advantages to us. We can put more memory capacity into our chips, right? So, and if you consider like today's important workloads, they are quite memory intensive, and obviously you need this DRAM density, and you need to push for it. You need to enable it instead of stopping it. So it's even a bit backwards looking. To find good discussion points, weaknesses are your friends. So you can start with each weakness that you identified. If you identify them right, then they can lead to good discussion points. And you can find fundamental weaknesses by asking, can we do better? In any aspect, basically. And of course, if you also discuss how to do better, if you pay some more thought, some energy on that. Okay. So I will give an example weakness here. This was one of the weaknesses that I listed over there. Memory performance attacks are not demonstrated on a real system. Okay, so this is a good weakness. So the discussion point can be like, should we do that? Okay, but this is just a starting point for a good discussion. It's not really the discussion point itself, right? It needs more work. So to make this a good discussion point, so you need to come up with a more structured way of organizing this thought. What is the benefit of demonstrating this? What research problem does it solve? Is it important to do that? Are there any papers out there that does this? Maybe this paper doesn't do that, but maybe some other paper does that. And if some other paper does that, what is missing in that paper? Like, what is the outstanding research challenge over there? We need to identify it. And what is your solution? Do you have any hypothesis, any key insights, observations, any key ideas, any expected results? So maybe you're familiar with some sort of implementation of some particular Intel processor generation, and then you have a unique way of mounting this attack over there, for example. So what are some practical challenges of doing that? Is it something doable? Is it something practical? What properties of the system we need to reverse engineer for mounting this attack, for example? Do we have real systems that implement studied or other row hammer mitigation mechanisms? So these are some like example questions that you need to answer, right? To come up with this discussion point. So it requires more work basically than just like asking some open-ended questions. And the key is again to be constructive, to ask, can we do better? Can we achieve something greater? How can we advance the state of the art? Okay, so here's my last example for discussion points. The font is unfortunately very small here. I hope you can see it. The example weaknesses, breakhammer cannot track an attacker across threads and processes. I mentioned this weakness in the list of weaknesses. So is this a problem? Yes, it's a problem because by leveraging this weakness, you can, by exploiting this weakness, let's say, you can bypass breakhammer via multi-threading. You might not still have no bit flips, but because there are some other row hammer mitigation mechanisms implemented in the system, but you can reduce memory availability and cause denial of memory service. So what you can do to do that is each thread activates a row a few times. The cumulative activation count of these threads on a row triggers the row hammer mitigation mechanism. But when breakhammer looks into each of these threads, it will think that, okay, yeah, these are just like memory non-intensive threads. They only perform a few activations. So maybe it will even accuse the actual benign workloads by causing those attacks, right? And then maybe some of them will be unfairly throttled. So ROHM mutations cause performance degradation and increase energy consumption. And practically you bypass break hammer becomes useless. So your goal here is to enable tracking row hammer based memory performance attacks across threads. So now we have a new research problem, right? Now we have a new goal that is beyond this paper. So let's discuss how can we achieve this goal. Let's say maybe we can come up with some hardware operating system cooperation. Breakhammer collects scores, the hardware level, and then exposes them to the operating system. Operating system has the context of all these software threads and then other like the concepts of processes and users, and it can follow some behavioral patterns of users and processes. And based on that, it can do throttling in different forms. One of them can be telling breakhammer to throttle by applying that quota to the cache miss registers. The other one is it can deprioritize the threads in the CPU scheduling. Another one is it can use some memory bandwidth allocation features of the modern processors. Now it comes, okay, we have a problem definition, we have a key idea, we have some idea of like how to achieve this. Are there other works that do this? So there's a similar work in the field. It was published in NDSS this year. So what it does is it's a software on the throttling, and it aims basically preventing bit flips caused by row hammer attacks. And as a software level mechanism, it can incur very high performance overheads, and it's opposite of what we want. But it does some throttling. It's software level, right? So there are some similarities, but there's some difference as well. So we can still find our niche novelty in this field. Okay. And the expected result is that we will provide an end-to-end solution to row hammer where bit flips are prevented within the DRAM chip by the row hammer mitigation mechanisms. And then we will have attackers stopped in the software level, in the higher level of the system stack, so that they will not incur extra overheads in our system. So this is like the kind of discussion point that I want to see, basically. I hope this gives a good example. And with this, I guess I'm at the end of my slides, and we have 3 minutes left. We can discuss more. Any questions? We can answer questions.
Are narrow, so does it allow for people to ask questions after our presentation? Because we have this 15-minute presentation, and then there should be the 5-minute critical review. So is there some time in between to do that, or would that count towards the 5-minute critical section time? How is it work?
So as I said, those time limitations are not really like hard limits, right? So you can go a little bit, but it's up from the break, of course, and it makes the class a bit longer. It's okay though. I'm happy to discuss more. So that 20 minutes is for your presentation of the paper. So you can consider that as like excluding the questions about the paper. And the discussion will be, so, okay, I have an example discussion point here, right? But it's not actually a good example because it was a monologue. So in a better setup, it should be more interactive. And interactive means like people will chip in and then they will also ask questions. You will also like maybe go back to the paper presentation, clarify some points, right? Q&A is more like in the discussion. That's the case. More questions?